All right, ladies and gentlemen. Let's
And even if some of it
guys. Hey, let's do some optics. Yay! Optics is fun. I got all sorts of lenses and mirrors and stuff up here you've been playing with the last couple of days. So this is a plastic lens that used to be in this device that used to be in pretty much all classrooms. What was it?
Oh, no, I was going to say, like,
You know what this is?
I saw something, it was like on like, they used a TV screen, like one of the big box TV screens,
Yep.
and they used the lens from that to make
An oven?
Yeah, or like
Yeah.
a sun laser too.
Yeah. Do you know what it is, Aiden? There used to be this thing that it was called an overhead projector, and it was a big light box, and they sucked. Anyway, it was a big light box, and it had an arm with a lens, and what would happen is the light would come up through this lens, and then it would project light. Basically, you put something that had like just outlines that were called transparencies, and they project light into this little convex lens, and it would project light onto the screen, and it sucked because the teacher would be like writing on the screen at this bright, basically this bright light, and then looking out into the classrooms like, everybody understand? And then people would be like, no, and be like, okay, let's move on, because he couldn't see you. Some teachers still use them in like backwater schools that don't have LCD projectors. But this is a really cool lens. It actually has a tremendously good refraction ability, and it's called a Fresnel lens. It's a Fresnel lens because it's a whole bunch of little etches in circles, circle, 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 circle. And if you were to look at the Fresnel lens, if you were to like zoom in on it, it looks like this. There's a bunch of triangles all etched into it. And it does the same thing as the lenses that you guys are familiar with. Where's my really good one? It's my really paired one. Yeah, one of these. So you could be like, woo, look at that, hey, optics. And you can go really close and like, nuggets outside, look at that. It's zoomed in. That's totally cool. This is really good for cooking ants and paper outside.
Yeah, my uncle taught me that.
Yeah. So
I ain't gonna lie, I did that.
No,
this one's a little trickier to use, but you get the same, you get the general idea.
Why then aren't you just the monitor?
Oh, good question. It's upside down because light moves in rays. Rays. All right. So yes.
Oh, no.
Okay.
You already said.
Yes.
so the top one's a convex and the bottom one's a concave, right?
Excellent question. Okay. So let's review our vocabulary. If something is caving in on you, like the inside of a spoon, which I, for a weird coincidence, actually have one in front of me. If something is caving in on you, it is concave, like the inside of the spoon. If something is caving away from you or bending away from you, it's convex, like the back of the spoon. So when you go home, you get a really nice shiny spoon, you can be like, I look different on different sides of the spoon, because one's concave and one's convex. The other thing we need to talk about is what light actually does when it goes through matter. This is pretty important. Okay? Now we know that when sound waves, which are longitudinal waves, travel through matter, they speed up or slow down. You go from air to glass, sound waves speed up or slow down. What do you think it is? So if you think a sound wave, when it goes through, like when the sound wave goes through this glass, if you think it speeds up, give me a thumb up. If you think it slows down, give me a thumb down. Sound wave. Okay, well, looks like we need to go back and teach mechanical waves again. When mechanical waves go through matter, they speed up. Yes, they speed up.
Wait, is this the sense of the matter, the quicker they go?
Yes. So for a mechanical wave, a little bit better. So this isn't a very shiny spoon, but when you go home today, get yourself a spoon and look at it, and you're like, I'm upside down, I'm right side up, I'm upside down, I'm right side up, I'm upside down, right? It's pretty cool. It's a neat little thing. If I had more spoons, I'd hand them out. Unfortunately, I only have one metal spoon.
Yeah, it's a good thing for you to be out joint spoon
Because some of the energy gets reflected. So some of my light, some of my mechanical wave energy is getting reflected off the glass, bouncing off my face, hitting the whiteboard, ending up with you, just bouncing around. Okay, so that's a mechanical wave that requires a medium. Now, an electromagnetic wave does not require a medium, meaning it can travel through space. But if it does have a medium, when an electromagnetic wave encounters a medium like glass, does it speed up or slow down? What do you think? When an electromagnetic wave like light encounters something like glass or water, does it speed up or does it slow down? Most of you realize, yep, it slows down. It's the opposite of a mechanical wave. So it slows down. And the reason it slows down is that electromagnetic energy has to be absorbed into one of the atoms and then spit out of the atom or molecule and then go to the next atom or molecule. So it's the difference between if I gave this ball to Alyssa and asked her to pass it down the aisle to Rachel. So I would just pass it as fast as you can to Rachel. Look at it go. It's going. That took like 4 seconds, and Rachel passes it to me. It's a lot. Oh, that was my bad. I got distracted. It's a lot faster just to throw it.
No, I know.
Okay. So light travels a lot faster if it can just travel through nothing. Make sense? All right. Now, another thing we need to dispel is, despite what you see in cartoons, those are or comics or pictures, and Superman, when Superman uses heat vision, light goes out of his eyes and melts the bad guy, or Supergirl, or Doomsday, or whatever. So does light go from your eyes to the object you're looking at, or from the object you're looking at into your eye? Yeah, so the universe, the environment, illuminates things that light reflects off of those things and ends up in your eye. So in this first diagram, there's a fish, there's a cat, and there's an arrow going from the fish to the cat. Is the cat looking at the fish, or is the fish looking at the cat?
Neither.
Cat's looking at the fish. So the environment is illuminating the fish, the light is traveling from the fish to the cat's eye. Oh, yeah. So light goes from the environment, ends up in your eye. Similarly, in this one over here,
The fish is looking at the cat.
yeah, the environment is illuminating the cat, the light's traveling from the cat to the fish,
But
and
isn't that because the water is reflecting the light? That's why you see two cats like fishes?
yep, and we'll talk about that in a little bit. Yeah, we'll talk about refraction just a little bit. Right now, I just want to nail down a few important things, like you understand that light doesn't go from your eye to things.
No, it totally does. The arrow's going.
Environment illuminates your face, and your face sends light to my eye, and I look at you and say, ugh,
They're not expelling.
because I observe the data of information coming from your eye.
And the arrow was like white.
Dude, I just need to finish the second.
Oh, that's cool.
Yay, Boulder City water, look at all those minerals, woohoo! All right,
So if the water didn't have minerals, it wouldn't be as much. You wouldn't see the beam.
yeah, you wouldn't see the beam quite as well if it didn't have the minerals. So,
It's good to know if you get water over there.
so, I'm sorry?
That water would be like the sort of.
Probably, but at the same time, I don't know what was in this container last time I filled it. Okay, I want to show you something interesting that we're going to talk about in a little bit. Okay, see the light?
Yeah.
See the laser going through the bottle? Pretty cool, huh? Look what happens when I change the angle. Isn't that bananas?
No.
How come the angle isn't going? How about the beam isn't? You know, if you can't see it here, let's add some silver. There we go.
Wait, are we talking like silver?
Silver.
Oh, damn.
So now you're gonna really see that light beam in here. That's silver. This is silver nitrate you're gonna use in your lab
Oh, sick.
later on. Maybe Friday. We'll see.
If you're an AP cam.
No,
No, in here?
in here. Yeah.
Oh,
So
yo.
now can you see it?
No.
Look at the angle that my laser is going in at the light. Look at the angle that's coming out. Isn't that bananas? So that has to do with the fact that light is traveling a lot faster in air and a lot slower in water. And look what happens when it reaches the top.
Yo, it looks like
Yeah, the light's coming out over there.
Yeah, some of the light is actually reflecting over there, and some of the light is ending up down there.
What the heck?
But none of it's coming up over there. There's no light popping up over there, which is kind of weird. There's a little bit, but as it, look at that. Now you're like, that's because light can't travel out of water. Well, if I do that, it can. Hey, look. It can travel just fine through the water if I just give it enough angle. But if I make the angle a little bit bigger, boom, stuck. It stays inside. That's called total internal reflection, a phenomenon we're going to investigate more in just a little bit.
Hold on, sorry.
You should.
Hey.
All right, so does it work with blue lights too? It sure does. It's just a lot harder to see.
I have more solar.
Add more solar.
That fixes it.
All right, so two kinds of lenses. This is a what kind of lens? Convex lens. We're not going to look at flat lenses because a flat lens is just a piece of glass. So this is a convex lens, and a convex lens is called a converging lens because light rays will converge to a point. What kind of lens is this?
Concave.
Concave lens. A concave lens is called a diverging lens because the rays spread out. Okay. Any more questions before we get into it? All right. Now realize we talked a lot about lenses because optics is primarily focused with how light travels through things, but we also got to talk about how light bounces off of things. So we're going to just start our discussion with the idea of reflection. Okay. And for this, I need a mirror like this. Whoa, this is one super dirty mirror. Wow. Okay. Did not.
You didn't plan this through.
It'll still work though. So I'm going to take this mirror and I'm going to duct tape this mirror to the whiteboard.
Still come.
All right. Then I'm going to walk over to the other side of the room and I'm going to take my laser. I'm going to shine my laser on the whiteboard and hit the mirror. And you tell me where do you think the dot's going to be. Okay, so I'm right here. And I'm going to shine my laser, it's going to hit the mirror, it's going to go boop. Point where you think the laser is going to end up.
So he's going to go Bob.
Are you right?
Bob.
Yes.
Yeah. There it is over there. So you've all encountered reflections because you've been around the world for a while and you know how mirrors work. And you've all played laser tag in your house and hidden in the bathroom, hidden in the tub and fired lasers off the mirror. Remember that? You guys have done that, right?
Yeah.
I did that.
If you've never done that, if you ever play laser tag with your friends, the best place for you to be is the bathtub. Because then you can shoot lasers off of the bathroom mirror and hit people as they walk by. You just go, and then they walk by, it's like, boop, boop, boop. It's like, you're nowhere near me. It's like, I'm around the corner. I can shoot around corners. And that's because of something called the law of reflection, which simply says, if you have an incident ray striking a boundary that is perpendicular to the normal, I'll explain what that means, the reflected ray will have the same angle. That's the law of reflection. So, a lot to unpack here, a lot of vocabulary. Incident is the ray that goes out. Reflected is the ray that bounces off of something. The normal, just like the normal in forces, is perpendicular to a plane. Remember that? You have a normal force. When you're sitting down, you have a butt force down, normal force up.
Yeah.
That normal force acts perpendicular to the chair.
Yes.
Okay. The normal force on me is acting perpendicular to the floor I'm sitting on. So a normal is a plane that is perpendicular to whatever the light is striking. So in that case, right there. Now, the angles of incidence and the angles of reflection are measured to the normal. Usually they're not just I and R. Usually they're given the letter theta I and theta R. So those angles. So as long as your normal is perpendicular to the barrier striking the where the rays strike, the angle of reflection should be the angle of incidence. They should be equal. That's the law of reflection. Now there is one more thing that you need to realize, and that is the media on both sides of the normal have to be exactly the same. The media has to be exactly the same. It needs to be air, air, or water, water, or gelatin, gelatin, or space, space.
Your mom, your mom.
Your mom, your mom. No, your mom is opaque. Your mom, there's nothing getting past your mom. Your mom is huge and opaque, so.
She's dead.
Wonderful. So anyway, these media need to be the same. If they're not the same, then the law of reflection no longer applies, but you almost always encounter them being the same. So far, so good? Okay, give me a thumbs up that makes sense to you. We gotta talk about it some more? Okay, so the incident ray that comes in and strikes the barrier, that angle will be the same as the reflected ray measured to the normal. So this is the normal, there's the barrier, and the angle of incidence is right here, and the angle of reflection is right there. And as long as there's the same medium here as here, air on this side of the room, air on this side of the room, and the normal, wait, where is the normal? Right here. That's the normal. So starting at the mirror, there's normal. So light goes in, boop, boop, and it bounces off. So the normal's right here. So this angle from here to where I was standing, that angle of incidence is the same as that angle of reflection. That's a law of reflection.
Yes.
Does that work for a curved mirror too? It does. Okay, so 3 types of mirrors. First one is the one you're all familiar with, the one you get up and see in the morning and you're like, I look good because I'm a sexy man. And you're like, yeah, you're like, yeah, that's a flat mirror. So 3 rays strike a flat mirror. What do? Yeah, they bounce back, right? That's what mirrors do.
Yeah.
What is the angle of incidence for each of these rays? 0. What is the angle of reflection for each of these rays?
0.
0. Simple, right? Okay, next, a concave mirror. There is a concave mirror right up there and a convex mirror right up there. I don't want to set them up here just yet because you can't see the screen, but they're right up there. So there's a concave and a convex mirror, big old fatties.
Shine a laser at it.
What happens if I shine a laser at it? What happens if I shine a laser at the concave mirror? It goes all over the place.
Oh, okay.
Yeah.
That is weird.
That's a concave mirror. So a concave mirror is a mirror that's curving towards you. 3 rays strike a concave mirror. What do?
They go like.
I thought
They don't
they
want set.
Well, let's draw a fun little couple of normals. The normal right here is right there. The normal here is right there, and the normal here is right there. This is actually pretty exaggerated. Let's try that again. So where is this middle ray going to go?
Straight back.
It's going to go straight back because pretend it's a horizontal line. Because that's an angle of incidence of 0 and an angle of reflection of 0. Now what about this one?
That one's gonna get an
That has an angle of incidence like that, so where is that ray going to go?
Down.
It's going to come in like this, okay? Because this angle of incidence is going to be that angle of reflection. Can you see that?
Oh, I can so see it.
Okay, let me draw it a little clearer with I'll use different colors. So let's say that and that are our normals. So here is our angle of incidence. So here is our angle of reflection. And the ray is going to come back. Yes.
Okay, so remember, I was talking to you about how like they used a screen or oven, whatever it was, to cook or make an oven.
Oh, sure.
This is what they use because it looks like it gets all the way, not all the rays reflect, but at like a certain distance from it, they'll all converge to one point.
Yes.
Okay.
Yeah. You see, we were talking about, everyone knows, like, you can use a magnifying glass to set paper on fire. You know what's really fun to set paper on fire? A giant concave mirror. This is a true story. About 15 years ago, I was at an AP chemistry workshop, and I was going through the equipment because I was bored, and I found a giant concave mirror in the back room, and I'm like, oh, this is awesome. So I took the concave mirror out because chemistry AP. Some of the chemistry AP workshops are really, really kind of loose and chill. So I took it outside, and I was going around, and I was like, "You're on fire!" I took the sun, like, "You're on fire! You're on fire! You're on fire!" People were like, "These chemistry teachers." So it was totally cool. I took a piece of paper and took a piece of wood, because you just aim the sun, and the sun's rays will come in. The sun's rays come in pretty much parallel. You realize that, right? I'll talk about that in a little bit. So they were hitting the mirror, and they were bouncing off. They were coming in and going pew, 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 and I put a little piece of paper right here, and it went whoosh, and then I put a little piece of wood there, and I can write my name. I'm thinking make a C. Yeah. So this is a concave mirror, pretty cool.
What a guy.
Can you build with that one?
I totally can, yeah. The tricky thing is, I don't have welding glasses.
Oh.
And I'm totally not going to set you outside with that thing, because as much as this laser cannot blind you, just FYI, a 5 milliwatt laser cannot blind you.
This is how it goes, guys.
If you want, you can come in after school and we can talk about protein reactions and how much energy would have to go into a cell to actually destroy cellular material. But this laser cannot blind you. That concave lens or that concave mirror can totally blind you. So I'm not gonna take that outside without welding glasses. 1 and 2.
I can bring you my welding glass.
Okay. Yeah, then we can take it outside if you.
Dude, that's big.
If everybody outside has welding glasses, then we can go outside and take it outside. But it is viciously bright, and in one false move, hey Rome, what are you doing? You're like, I'm going to the hospital.
You're a professional gamer, Rome.
Anyway, so we can agree that the 3 rays come in, and then they do something called converge. Okay, those rays come in and they converge to a point. That point is a special name. Anyone know what that point is called? Focal point. Yeah. It is the focal point. It's a point at which something converges.
And then when we were talking about the focal length, that's how far you have to be to get that focal point?
Exactly, yes. So if that's the focal point, that is the focal length.
Dude, you just sounded so smart, Rome.
Dude, that's the first time.
Yeah, write it down. Senior quote. You just sounded so smart, bro. Okay, convex mirror. Now things are kind of interesting with a convex mirror. There's a convex mirror up top. If I shine the light on the convex mirror, I like to call this the 7-Eleven mirror or the Walmart mirror. If I shine light on the convex mirror, the light does bounce off, which is kind of goofy. So again, these have normals, there,